So in this presentation, we're going to focus on the relationship between the force on two different charges. So we know that like charges repel one another and unlike charges attract one another. And we'd like to focus now on how big is that force and what does it depend on. So Charles Coulomb in the 18th century discovered the relationship between charged particles and the force that they exert on one another. And this is called Coulombs Law. And so the mathematical relationship is that the force that is exerted on each of the particles, and this is the magnitude of the force only, is equal to or depends on each of the charges. So Q1 and Q2 represent the charges in units of coulombs on each of the different objects. And then, so the force is directly proportional to each of the charges, and it's inversely proportional to the distance between those charges squared, where that distance is measured in units of meters. There is a proportionality constant out front, K. K is called Coulomb's constant. It's always exactly the same value, which is 9 times 10 to the 9 newtons meters squared over coulombs squared. So the force can be an attractive force or it can be a repulsive force depending on whether the charges are like charges or unlike charges. And the force always acts along the line that connects those two charges. So let's see if we can explore some examples of Coulomb's law and look at what happens if you change the force. So we have our expression for Coulomb's law here, and we'd like to know what happens to the force between two charged particles when the distance between the charges doubles. So suppose I put charge on each of these objects, and I have a PhET simulation that I'm going to pull up, but here is a picture of that PhET simulation. In this particular picture, there is zero force on those charged objects because one object doesn't have any charge on it right now, right? So the first object here has zero charge. The second object actually does have charge on it. So how do we look at this example? How do we look at something when we want to know what happens to a quantity when you double one part of the quantity that you're looking at? So the first thing, the best suggestion that I have is to put some numbers in. So let's assume that the charge on the objects Q1 and Q2 is just 1 Coulomb. We can make it any number we want, but why not make it something simple like a 1? So each of the charges have a charge on it of 1 Coulomb, and let's make the distance between the charges be 1 meter. Again, just using an easy number 1. So if I apply Coulomb's law, F, that force between these two charges of 1 Coulomb that are a distance of 1 meter apart, would be Coulomb's constant. I'm not going to put Coulomb's constant in, I'm just going to leave it as a K, times each of the charges, Q1, Q2, so 1 times 1, over 1 meter squared. If I square 1, I get 1, so I have 1 times 1 over 1 is just 1. So the force between those two charges that are separated by 1 meter is just some quantity K, which is just Coulomb's constant. So the question is, what happens when the distance between the charges doubles? So the charge on the objects is staying exactly the same. It's still 1 Coulomb, but the distance between the charges is now twice what it was before. So instead of being 1 meter, it's 2 meters. And we can plug those values in. So we have the force is Coulomb's constant, charge 1, charge 2, over the distance of 2 meters squared. 1 times 1 is just 1, but when I take 2 and I square it, it gives me a 4. So I end up getting that the force is now 1 over 4 times K, or more specifically, if I double the distance between the charges, the force has actually decreased by a factor of a fourth, right? So it was K, and now it's 1/4 K. So if you double the distance, because the distance is squared, it decreases the force between those two charged objects by a factor of 1 over how you change the distance, changed it by a factor of 2 squared, which is a fourth. So if this had been what happens to the distance between the charges if I triple the distance, if this had been a 3, then this would have been a 3 squared. 3 squared would have been 9. It would have been 1/9. So the force would have been 1/9 what it was to start with. Let's consider another question. So what happens to the force between two charges when the distance between the charges is kept constant, but the charge on each particle is doubled? So we go through the same process. We say that each of the charges start off with a charge of 1 Coulomb and a distance between them of 1 meter. And so if I find the force, just like before, I put in each of the charges, divide by the distance squared, which is 1, squared is 1, so the force is just K, Coulomb's constant, right? Because everything else is a 1. But now the question is, what happens if you double the charge? So now instead of 1 Coulomb on each charge has 2 Coulombs, but the distance between them remains 1 meter. So I plug in the force, and the force is Coulomb's constant times each of the charges, which are each 2 Coulombs, over the distance between them squared, which is just 1 squared is 1. So 2 times 2 is 4 over 1. So the force actually increases by a factor of 4, it's 4K compared to what it was before. So this is a way that we can look at analyzing a question that says, well, what happens to this quantity if I double this other quantity? And it's just nice if you just put some numbers in, some easy numbers, and then compare them to see what happens. So one of the things that we can do is we can check this out with the simulation. So I have the PhET simulation here. Right now they have 0 charge on them, and I'm going to go ahead and I'm going to bring them so that they are exactly, this is in centimeters, so it does, the units are going to be a little weird, but we can at least see what happens. So let's put 1 Coulomb of charge on each of these. So they each get 1 Coulomb of charge, and actually, let's just do it that way. Okay, there we go. So they're separated by 2 centimeters. They each have 1 Coulomb of charge. Let's actually make it something like 4 on each. There we go. So it's around 360 newtons of force. They're both positively charged, so they're repelling one another, and these people are like holding these objects back. That's why there's this line connected here. So the question is, what happens if we double the distance? So it was 360, and if I double the distance so that now I move this one out to 8, the distance is around, or the force on those charges is around 90. So the force has decreased by a factor of a fourth. Right? So it was 360, and now it's only 90, which makes sense according to what we saw before. So let's put these back together again, and let's put the force, let's put the charges at 2. So if I have these 2 charged particles, they're separated by some distance of 2 centimeters, and I leave that distance the same, but I double the charge on each one, so it was 2 microcoulombs on each. The force is about 90 newtons on each one. If I double the charge on each one, so that now it's 4 units of charge, the force becomes 360. So the force has quadrupled, right? It has increased by a factor of 4. It was 90, now it's 360, so it has increased by a factor of 4, which is what we saw when we looked at this in terms of different numbers, but we can see this with the simulation as well. So by doubling the charge on each object, it increases the force by a factor of 4. If we double the distance, it decreases the force by a factor of a fourth. So one of the things that you may have noticed in the simulation is that the units for the charge on the object was not coulombs. It was actually something called microcoulombs, and that's because 1 coulomb of charge is extremely large, and it's very unusual for us to talk about an object being charged with 1 coulomb of charge. So let's look at how many electrons we would actually have to have removed from an object in order to get a net charge of 1 coulomb, right? So if I remove 1 electron from an object, then what's left behind are, there's 1 more proton than electron, so I would have only 1.6 times 10 to the minus 19 coulombs of charge. So the question is, how many electrons would I have to pull off? If I pull off 2, then I have twice that amount, so twice 1.6 times 10 to the minus 19. 10 to the minus 19 is a really small number. So let's see if we can figure that out. So charge in general on an object is just the charge of the electron multiplied by how many electrons you actually add or remove, right? So if this were 1, if I removed 1 electron, then the charge on the object would be just the charge of an electron, 1.6 times 10 to the minus 2. If I remove 2, like I said before, then it would be twice that, so 3 times 10, and so on, right? If I remove 100 electrons, it would be 100 times 1.6 times 10 to the minus 19. So our question is, if we have 1 coulomb, if we want 1 coulomb of charge, how many electrons do I have to remove in order to get that, where each electron has a charge of 1.6 times 10 to the minus 19 coulombs? So in order to solve for n, I can divide both sides by 1.6 times 10 to the minus 19. So 1 coulomb divided by 1.6 times 10 to the minus 19 is the number of electrons I would have to remove. If I divide those numbers, 1 divided by 1.6 times 10 to the minus 19, I get 6.25 times 10 to the 18 electrons. So to get 1 coulomb of charge, I would have to remove 6.25 times 10 to the 18 electrons from an object. That's a huge number, right? 10 to the 18 is just a huge number. So we typically do not use coulombs in our units. That's the standard unit, and so when we're using Coulombs law, we have to actually have our charge in units of coulombs, but most of the time objects will not be charged with that amount of charge. So other units of charge that we typically use are something called microcoulombs. 1 microcoulomb is equivalent to 10 to the minus 6 coulombs. So if I want to convert units from microcoulombs to coulombs, I just have to, every time I have a micro, I replace it with 10 to the minus 6. You can also use your calculator, and you can use the E or the EE function on your calculator, and you can write 1 microcoulomb. You would write this as 1, and then use that E or EE function, and then put a minus 6, and that writes everything in scientific notation. So one of the things that you do need to be careful of when you're using really small numbers or really big numbers is making sure you put it in your calculator correctly. So if you're unsure about how to put it in your calculator, you can look that up, or you can just use lots of parentheses. So make sure that if you have something that is raised to a power, that you put parentheses around it. So let's look at another example problem that would be similar to a homework question. So we have 2 charged particles. The first one has a charge of 15 microcoulombs, and the second one has a charge of 30 microcoulombs. And they're located at a distance of 0.2 meters apart, which is equivalent to 20 centimeters. We want to know what is the force between these charges, and we want the units for force to be in newtons. So the first thing I realize is that my charge is in units of microcoulombs, and in order to use Coulombs law, I have to have my charge in units of coulombs. So I can convert Q1 from microcoulombs to coulombs by replacing the microcoulomb, here's my microcoulomb, with 10 to the minus 6. And then I can do the same thing for Q2, where I have 30 microcoulombs. Where I see micro, I replace it with times 10 to the minus 6. Now I can use those values for the charge, and I can plug in. So according to Coulomb's law, the force is equal to Coulomb's constant. Coulomb's constant is a number that doesn't change. It's 9 times 10 to the 9, has units of newtons meters squared over coulombs squared. And then I would multiply that by 15 times 10 to the minus 6 coulombs for Q1, 30 times 10 to the minus 6 coulombs for Q2, and then I'm going to divide by 0.2 meters squared. So if you were putting this in your calculator, of course you don't have to worry about units, but if you use parentheses here, you will get better results in terms of how your calculator is functioning. A lot of people make mistakes when they're putting this bottom number in or not using the correct parentheses. So if I multiply all the quantities that are in the numerator, I would take 9 times 10 to the 9, 15 times 10 to the minus 6, 30 times 10 to the minus 6, and I would get 4.05. The coulombs and the coulombs cancel out with that coulomb squared, which gives me newtons meters squared. And then when I square 0.2 meters, I get 0.04, so 0.2 squared is 0.04. And then when you have to square the units, you get meters squared. So that meter squared and that meter squared is going to cancel. I'm going to end up with units of newtons. So 4.05 divided by 0.04 is 101.25 newtons. The next question says, what is the force between the charges when the distance between the charges doubles? We should be able to answer this question without putting any numbers in, because we know that if you double the distance between the charges, the force decreases by a factor of 1/4. So let's just check it and see what happens. So Coulomb's constant is still 9 times 10 to the 9, Newton meters squared over Coulomb squared. The charges have stayed the same, and so 15 times 10 to the minus 6, 30 times 10 to the minus 6, and then divided by the distance squared. I have doubled my distance. My distance was 0.2, now it's 0.4, and I have to square it. So the number at the top, multiplying everything in the numerator, is still the same, but when I square the 0.4, I end up getting 0.16, and then when I divide, I get 25.3125 newtons. So this number here is about a quarter. It is a quarter of what the force was originally. So if I double the distance, I decrease the force by a factor of 1/4.